faculty member at BITS Pilani Goa campus. Prior to joining BITS, he was also with a faculty member at Kazakhstan and also at Hyderabad. And then if more than anything, I would encourage all the FPGA enthusiasts to look at his YouTube channel. I think some fantastic videos and all the getting started and hardware debugging, very well recorded by Vipin. I think we also look at it many times. Thanks for joining us for the winter school. Over to you, Vipin.
Okay. So first of all, thank you very much, Mozilla, for having me. So anyway, introduction you have done. So I'm personally assistant professor with BITS Pilani, Goa campus. I mostly work on FPGAs, is in reconfigurable computing. So most of the work is also in reconfigurable computing. So in this presentation also, what I'm trying to bring is this idea of FPGAs or FPGA-based computing into computer architecture. I guess there was already a presentation by Mathura regarding FPGA-based accelerator. And this presentation is actually somehow an extension of previous presentation by Dr. Manu. So you'll see the similarities here. Another thing, since personally I cannot sit in a lecture for more than 30 minutes, I have made this lecture also like that. This is a short one. The main idea is to introduce the concept of in-memory computing and to motivate you to this domain. So a lot of research is already happening in the domain. So basically this will give you an introduction. I wanted to do some hands-on also, but since the time is limited and for FPGAs, things take a lot of time for compilation, not like our traditional software flow. What I have done is, as Madhura said, I have put a link to my YouTube channel. So the things which are discussed here, there are hands-on tutorials there. So I will encourage you to go there and try some of them out. And if you face any issues there, you can directly contact me. Directly contact me better. Okay, so let's get started. So the topic is in-memory computing. That's the main topic, small with FPGAs. Now the term in-memory computing, if you look at the literature, this term has been used in different sense now, and it was used in a slightly different sense a few years back. So if you read the papers from a few years back, this in-memory computing that was mainly motivated by databases, the implementation of databases. So that is one way. This is an extension of previous lecture, because large databases, they were kept in non-volatile memory, our traditional HDDs that time. And the access time for these databases, it was quite large. So to reduce it, there was an idea proposed like we keep them in maybe in your main memory itself. And the papers were discussing about what are the algorithms we need to use, what are the architectural changes we need to make to do that. Okay, that was the meaning of in-memory computation a few years back. But currently, the whole term is used in a different sense. So in this presentation, I'm going to use it in this new sense. So what is that sense? We'll see as we go along. So what is the main motivation for this in-memory computation? The main motivation is indeed the amount of data that we have been generating in current scenario. So it is estimated that we are generating about 2.5 exabytes of data every day. And 90% of the data in today's world that has been created in the past 2 years alone. So there is a tremendous amount of data being generated by all the computing application, whether it will be online video streaming, or whether it be AI, whether it be IoT applications. We are generating a large amount of data. And the global scientific output, that is doubling every 9 years. So there is tremendous amount of data. That is one major motivation for looking at in-memory computation. So two things which are fueling this is one is Internet of Things. As you know, IoT, now we have internet or some version of internet, even if there is no internet, some packet-based communication coming into all kinds of appliances, whether it be your TV, whether it be your washing machine, everywhere this packet-based communication or internet-based control communication, that concept is coming. So that is generating, again, huge amount of data. Okay, so by 2020, it is estimated like 30 billion devices are connected through IoT. And the amount of data generated by them is like 40 trillion gigabytes. Again, huge amount of data coming there. Now, another field which is scaling is AI. So in many cases, IoT and AI, they go in hand also. But anyway, so here you can see the major revolutions in the history of mankind. So we had like our industrial revolution, maybe in 16th, 17th centuries. Then there was invention of steam engine. Then we have electricity, steel, then automobiles came. Then we have information technology coming in the late 80s, 90s, 2000s. And presently we are in the era of AI. So this is also generating huge amount of data. Not only huge amount of data, the computing power that is required by AI is tremendous compared to other computing paradigms. That is mostly because here we are trying to emulate human brain itself. As you might be knowing, our brain, it is quite parallel in nature. It can do many things in parallel, although we don't really feel it. The architecture is quite parallel in nature. So that's also generating a huge amount of data. Now the question is, when we are trying to emulate this brain using our traditional computing platform, so that we usually mean our CPU based, right? Whether it can achieve the required performance, whether our traditional von Neumann based computing paradigm is that suitable for AI based applications. And it seems like that is not that suitable. That is one issue with our von Neumann. We'll see why. Now, this is one best example for our AI, power of AI. So IBM's Watson supercomputer, it has defeated two human super champions in a game called Jeopardy. Now, another question comes here is, so the machine is quite powerful, the supercomputer. It has like 2,880 processor threads and 16 terabytes of RAM. That sounds good. But the bad part is this is using about 80 kilowatt of power. And the power consumption of human brain is approximately in the order of few watts. Usually we say like 20, 25 watts. That's the brain power. That's the power consumed by our brain. But the power consumed by the supercomputer is in the order of several kilowatts. So why this is happening? This is mostly happening, although this is a supercomputer, this is also following the traditional conventional von Neumann computer architecture, which I guess you have studied in your computer architecture course. So here mostly the idea is we have a processor and we have some kind of memory, maybe a main memory. I'm giving a broad overview. You can have different levels of paradigm memory. Maybe your cache, main memory, things like that. But we just abstract and show it as like the memory. So your code and data that is sitting in the memory, the idea is the CPU, it fetches code and data, it executes it, and maybe write it back to the memory. So if you ask in a computer, where is the maximum amount of power consumption coming? That is coming in this movement of data between CPU and memory. Okay, that's the part which is consuming most amount of energy. And that is one reason why the supercomputers, they are these power hungry. Now, when we come to AI, okay, so this is the current landscape of AI algorithm. So at the bottom, we have this so-called deep learning, where we have multi-layer neural networks. On top of that, we have this machine learning. The difference here is maybe not very accurate definition, but we can say like in machine learning, maybe this is more like unsupervised. A machine is trying to learn itself, kind of thing. And the machine learning algorithms, they are usually implemented using some deep learning architecture. That architecture can be in pure hardware or it can be pure software based. So if you look at the hardware which is employed for implementing these algorithms, CPUs are there, of course, but in recent years, GPUs are becoming more and more popular for DL and ML algorithms. Because the reason I have already mentioned before, these algorithms, these architecture, they are highly parallel in nature. So GPUs, they are also like more or less inherently parallel in nature. Maybe you have again studied in your courses. GPUs, they have many small processors. They may not be as powerful as the processing core in your main processor, but that makes up in the numbers, right? There will be thousands, tens of thousands of small, not very powerful, but small processes which can run in parallel. That is actually bringing the power of GPU. So it is very suitable for implementing these kind of parallel algorithms. FPGAs, maybe not that popular. Maybe in academic publications, we can see many papers where FPGAs are also used for implementing ML and DL architectures. But practically, they are not that popular. Maybe reasons we can discuss. But if you have any formal experience with FPGAs, the major challenge, is first of all, writing your own custom hardware for implementing on FPGA, that is challenging. That is one reason. But nowadays, again, FPGA vendors themselves, they are developing AI algorithms as well as machine learning algorithms, which are specifically targeted for FPGA. So if you go to Xilinx website, now you will see like they have developed their own software package called this Vitis AI, which has set of APIs, Python based. So you don't have to, at least by their claim, you don't have to know anything about hardware. You just have to be some expert on software, some expert on neural network in general, but you don't have to know much about hardware. And using these Python based libraries and HLS based coding, you can easily implement these neural networks on FPGA. Okay, that claim is there. So maybe it may become popular to some extent. But here also the main issue that is coming is currently all these architectures, they are still more or less following our traditional von Neumann architecture. So in case of a GPU, if you have done CUDA programming, what you do is, yeah, of course, you will be writing the kernels for GPU, which will be running on the GPU. Now the data which has to be processed by this GPU, that will be again initially stored in the main memory of your system. Then you will be making some memory copy API call, where it will be copied from your main memory to the GPU. Then the GPU will be executing it parallel. That is quite fast. After that, this data has to be again moved from the memory of the GPU to the main memory of the server, wherever it is running. So this data movement, that is again consuming power. And that is also taking time. So the time required for this data movement, maybe that is much larger compared to the actual computation time. In case of FPGAs also, that is the current scenario, because the FPGA accelerator boards, I'll be showing the example later, they are also coming with this PCI Express interface. So you will have this FPGA cards, you will plug it into some server, you will have your hardware on FPGA implemented. Then you transfer data again from your server to the FPGA accelerator through PCI Express. FPGA will be processing it, you will send it back again to the system. Again, this communication overhead, it may outweigh the processing time. Okay, so that again makes things slower. So this modern complex machine learning algorithms, that may take several weeks for just the training part. That also means they are going to consume huge amount of power. So all these are what is actually motivating us to go for in-memory computation. So I'm also showing some market cap of the hardware which we are currently using for this AI. So you can see, like, as we go along, the market share for ASIC, application-specific integrated circuit, that is going to be going way higher compared to the market share for CPUs as well as market share for GPUs. Okay, so I guess you understand what is meant by this ASIC, right? ASIC usually we mean a integrated circuit which is developed for a specific application. For example, this is quite famous, our Google TPU, Google Tensor Processing Unit. So Google, they have developed this TensorFlow library, which became very popular in implementing our deep neural networks and machine learning algorithms. Now, again, that's, as I mentioned before, it's quite parallel in nature. And our traditional CPUs, they are not very suitable for that, but you can do some acceleration using GPUs. But what Google did was they went ahead and they created some chip called the Google TPU, Tensor Processing Unit, which are specialized for processing these tensors. So tensor is nothing but it is a multi-dimensional matrix. So these things, these piece of chips, they are very specialized for processing matrices, especially multi-dimensional matrices. So that will give you immense throughput and the speed of training, as well as later when you are testing something, that is much, much higher compared to our traditional implementation. Now, of course, ASIC drawbacks might be known to you. The initial engineering cost, that is extremely high for ASIC. That will be making the cost of the chip also quite high, provided they are not produced in hundreds and thousands and millions like our CPUs. So TPUs are quite expensive. Similarly, Microsoft, they have their own chip. NVIDIA, they have something called Tensor Core, which is again for accelerating TensorFlow. Similarly, IBM, they have their own chip also for accelerating this application. Now, if you see in the overall market, contribution of FPGAs, that is very, very small. Is there any issue with audio? Can you hear?
Yes, sir.
Yeah, okay, thank you. So the contribution from FPGA is quite small. So as a person who is working in this domain, my motivation is to increase the market share for FPGAs and make it more popular for AI implementation or neural network implementation. Now, the advantage of FPGA is, again, maybe you have studied, it is somewhere in between a SIC and our traditional CPU. Yeah, so the cost of development is not that high for FPGAs because the chips are already manufactured in large number. So the per chip cost is relatively less. And at the same time, this is programmable. Right? So the risk associated with ASIC development, that is quite less in FPGA. If you make any mistake, if things are not working, you can just go ahead and debug it and reprogram it, and it will work. And it is parallel in nature. That is another huge advantage, right? Because the hardware that you implement on FPGA, you can again implement many processor cores if you are going with processor kind of implementation, or if you are using something called the systolic array or CGRA-based implementation, that can also be implemented on FPGA. So things can run in parallel also. So it seems like this is a quite suitable architecture for implementing this, but still it is not very popular. Now, again, there are many reasons why it is not popular. One reason I mentioned last time, because ultimately, although FPGA is quite powerful, the time for transferring this data between your system and the FPGA, that is quite high, usually, relatively high. Okay? When I say like high, it will be in terms of few milliseconds. But still, it is high, relatively. Another reason is the logic capacity that you can have in an FPGA is limited. Okay, so you have a very huge neural network with thousands of, let's say, millions of neurons in the network. And if you want to implement it on an FPGA, might not be possible because how much logic is available inside the chip is limited. So you can implement a net only that big. You cannot go beyond that. So that is another drawback of FPGA. And of course, the time required for development, that is also relatively higher compared to your software implementation, but it is definitely less than going with a custom ASIC implementation. So that is that. So what I am trying to do is trying to mitigate this negative, what do you say? Let's say like features of FPGA so that it can become more popular in implementing AI algorithms. Okay. So till now, the term in-memory computing hasn't come. It will come soon. Okay. So before going that, again, we are going to look at this Dennard scale. So this Moore's law, you might be very familiar with, right? Which was proposed like the number of transistors in the chip will double every 18 months or 2 years, like that, right? And we have been talking about the end of Moore's law for quite some time, because as we are making the size of transistors smaller and smaller, so that we can pack more and more transistor inside the same chip, what is happening as the size is becoming smaller and smaller? Yeah, of course, power has a huge impact there. We'll say like we are hitting the power one, because the size is so small that the power, the heat generated in the chip, that is enough to destroy the transistors inside the chip itself. So we cannot minimize or miniaturize the transistor beyond a certain limit. That is one part. Another part is when you are making transistors smaller and smaller, our traditional Kirchhoff law, they won't work anymore. You go it smaller and smaller, there will be more and more quantum effect coming into the transistor behavior. So our traditional circuit modeling or simulation or design implementation techniques, they are no longer working. So that is one challenge faced by Moore's law. Okay? That's what we say as Moore's law. This Dennard scaling, this is actually coming in the design of memory, actually, mostly. Also in chips also, CPU also. So what was proposed in Dennard scaling was, as the transistors get smaller, their power density stays constant. This is the postulate of Dennard scaling. That means you take a chip and you reduce the number of transistors there. Of course, you can pack more and more transistors into the chip. And it was expected that the power density will remain constant. Power density is not going to change. Power density basically means, yeah, how much power per unit area. Okay? So that is not going to change. But you can see here also, in late 2000s, this rule or this scaling has also started to fail. The power density is no longer staying constant. The power density is keep on increasing as we are making transistors even more and more smaller. So there is a limit beyond which we cannot make them smaller. That means we cannot make what we say like a more complex chip beyond a certain level. We won't be able to increase the memory capacity if we are designing a memory chip, DRAM or SRAM, beyond a certain limit because of this issue. Another thing, and this has been known for quite some time, the performance gap between the processor and the main memory. So from long time ago itself, the research in the processor design, that was much more intensive compared to the amount of research that was put into memory design. So here you can see as years passed, the performance of CPUs, that is more or less keeping in line with the Moore's law, that is keep on increasing. But the performance of the main memory, that is not scaling in that level. Okay, one reason is, yeah, of course, the companies who are working in memory domain, that was limited. The amount of research that was happening there, that was also limited. And of course, the limitations from technology perspective, that was also there. Anyway, because of that, there is a huge performance gap between your processor as well as memory. This is another bottleneck when we are going to implement our AI algorithms, whether using it CPU, whether using it GPU, or whether using it in using FPGAs, as long as your data is stored in the main memory somehow, and from there it is being transferred. So all these platforms, they are facing this issue, the limitation by the memory, the performance limitation of our traditional memory design. So this is what is, what is a motivator for in-memory computation. Okay, so what is happening in in-memory computation? So here, one example is given. So the left one is our traditional computing system. We'll say like one human computing system, right? So suppose here you are using an operation like, let's take a simple example like y equal to x plus y. Okay. So how this is going to execute? So if you want to implement this, again, bird's eye view, you'll be storing your variables x and y somewhere in the memory. Okay, this is your main memory. Maybe your x is here, maybe your y is here. First of all, what you will do, assuming these things are not already in the cache memory, this is your main memory, okay, your DRAM. So your processor, he will be making a read request. He will get maybe X and he will store in his register. Then he will make another read request. He will get Y. Again, he stores in his internal register. Then using ALU, he adds them. Then it will do a write operation to send it back to the main memory. Okay? So that's how it is implemented in our traditional system. So here, this reading from memory and writing to the memory, that is the main bottleneck in the performance. As I mentioned before, that is going to consume power, as well as the latency involved in that one is quite high compared to the actual operation that you are applying on them. Now, to improve this, initially we introduced this concept of cache memory, as you know. So we have high-speed SRAM, which is sitting in the processor chip itself. If it is L1, L2 cache, it might be on the same chip itself, which can give you some improvement to some extent. But as I mentioned before, in AI implementation, huge neural net implementation, we are talking about millions of data points. So there, if you look, the amount of cache misses, that is quite large actually. So what happens in many cases, if things are not properly done, the cache will be actually hitting the performance instead of giving you performance improvement. Okay, but if done properly, if analyzed properly and proper caching is applied, you may get some improvement. But still the memory is causing a huge bottleneck here. Again, another reason why this is happening is our traditional memory, our RAM, physically that has a single port actually, a single port. That means here, if you see, if I have X and Y at the same time in my CPU, I can add them, no issue. But when I'm initially accessing them from the main memory, I cannot read X and Y at the same time. I can only read only one variable first, then only I can read the second variable. Why? Because this has only one physical port, right? You know the operation. So I have to give the address of X, then I get X. I have to give address of Y, then I get Y. There's no way like I can get X and Y at the same time. So there has been what we say specialized memory with multiple ports where you will be able to read multiple data concurrently. Of course, in FPGAs, we do those kind of memories. But in our traditional computing system or the commercially available memory chips, this feature is not there. You have a single port and you have to do it sequentially. So that is creating a bottleneck. Now, to overcome that, what is proposed is if you can implement some kind of computation within the memory itself, maybe it will improve the performance. Okay, that is the proposal. So basically, we do some computation in the memory itself. That is what we call as in-memory computing. So same system with some modification. Here you can see. So this memory, this has a conventional memory like the one we discussed here, which is used only for storing data. Then we have something called this one, computational memory. That means the memory which can do some kind of computation also. So in this system, if you want to do x plus y, how will you do? The x and y, they are already in the memory. Okay? You will be only sending a control signal saying like, I need to add these two variables. So he will be adding these two variables, x and y, within the memory itself. It is not coming to the processor. The addition operation happens inside the memory itself. Then that will get stored in the memory itself. So this can hugely improve the performance because if you see the number of transactions here there was a two read operations and one write operations happening. Here, maybe just one control asking to addition operation. One control signal is going. Maybe basically the addresses of the variables and what operation should be done. Only that information is being passed from the processor to the memory. So this will greatly improve the system performance. And this is what we mean by in-memory computation in the present scenario. Okay, computing within the memory itself. I hope it's clear. If you want to ask anything, stop me at any point. It's okay? Okay. Yeah. You want to ask something? Yeah. Okay, so this is how in-memory computing is defined. Okay, so in-memory computing means design approaches that performs computations close to memory to overcome memory bottlenecks. Okay, so in-memory and close to memory, these terms are also used interchangeably also or together most of the time. Instead of doing it exactly in the memory, close to memory also. That's fine, but I'm using this term in memory. So implementing this kind of memory with our traditional memory cells, like using our SRAMs or DRAMs, or using our traditional design techniques following CMOS design technologies, that is very challenging because CMOS technology that has been very specialized for storing data in the memory. Okay, so that may not be very suitable for implementing these kind of computational memory. Maybe we can do it, but the impact might be, this will be taking a huge chip area. Yes. Yeah. So that will be that computational memory, the computing part that might be taking a large chip area, which may affect the overall memory capacity. So because of that, we need to develop new technologies for implementing these memories also. Okay. So we won't be going with our traditional CMOS-based implementation, whether it is SRAMs or DRAMs. So here you will see the terms which were introduced in the previous presentation also. So for implementing in-memory computing, these are the new techniques which are being proposed. We have our RAMs, PCMs, phase-change memories, and Memristors. There are many techniques. I have listed only three of them. So I'll be just going through some basics of this one, Memristor, because again, a lot of research is happening in Memristor field also. Again, especially Memristors are becoming more and more popular because it seems like they will be the best candidates among these newer technologies for implementing neuromorphic computing, or basically for implementing neural networks. So many people are working on it. So maybe let's quickly have a look at Memristor. Then I will come back to the previous slide. So Memristor, it is told like this is the fourth, what you say, fundamental component in electrical design. So resistor, capacitor, inductor, we are all very familiar with them. They are widely used in our circuit design. But this fourth guy, we have hardly used it. But it has been proposed quite early, like in 1970s itself, that there should be one more fundamental component in electrical design. Because if you see these fundamental components that we are presently using, they are always associating maybe two kinds of electrical parameters. Because as you know, resistor, it is relating between voltage and current. Capacitor, that is relating between voltage and charge. Inductor, that is between current and flux. So the only thing that is missing is some component, basic component, which is relating charge with flux. And that is what is called as a Memristor. Okay, so this is a device which somehow correlates the charge and the magnetic flux. How it correlates, we'll see soon. And this is basically the symbol used for Memristor. From the name itself, you can find out. So Memristor basically means memory plus resistance. Okay. So it can somehow memorize resistance. That is what we meant by Memristor. So it's a contraction of memory resistor. If you look at the equation quickly, this is how the flux and charge equation for Memristor look like. So M is what we call as the memristance. So the resistance of a memristor, that is what we call as memristance. So unlike our traditional resistor, right, we say like a resistor that is a passive component because it has no memory, it cannot remember what happened in the past. Memristor is a different guy. He is also having resistance, but that resistance value is not a constant resistance. That resistance value depends upon the flux and the charge, the relation between flux and charge. And this is how that relation looks like. M is d phi by dq. Psi or phi, whatever you like, you can put it. Okay, so this resistance changes based on the rate of change of flux with rate of change of charge. Now, if you look at the dimension of it, ultimately the dimension is V by I. So the unit of memristance, that is also unit of resistance. So basically this is like a resistor, but this is like a resistor with memory. He can memorize what happened in the past. Or basically his resistance value depends upon what happened in the past. Okay. Now exactly how Memristor works, maybe I will not go into the details. Maybe you can read later in the slide. Basically, that is working based on how it distributes the oxygen deficiencies in a titanium dioxide. And titanium dioxide is actually not it's a conductive material. It is a resistive material, and there is a conductive material also. So based on this, how these oxygen deficiencies are distributed, based on that only its conductance, or basically its resistance will change. So that conductance we can change by applying a voltage across this memristor. So maybe if we apply a positive voltage, there will be more conductance. That means its resistance will reduce. But if you apply a negative, its conductance will reduce or the resistance will increase. Now, the interesting thing is, even if you remove this voltage, which change this resistance value, the distribution of these deficiencies will remain there. Or basically, he memorizes his resistance value, even if you remove these voltages. So that's how basically Memristor comes. Now, why Memristor is becoming more popular? For that, we'll quickly look at our traditional neural network architecture. Again, you might have seen this figure many times. So basically here I have shown a feed-forward neural network. So all these circles, they are like neuron. So basically what is happening inside a neuron? The most important operation that is happening inside a neuron is a dot operation. Basically a matrix multiplication and accumulation operation. So here you are giving some input to the neural network. Maybe we can call them like feature set. That is what you are feeding here. Now, inside each neuron, there will be something called some weight values. So how we get these weight values? We are getting these weight values through something called the training. Again, details I will put in the YouTube video, those who haven't heard about it. Many of you might be knowing. So basically this guy, he has to multiply these input values with these weight values and sum them up. Yeah, so same operation will be happening in all the neurons. And if we can implement them in parallel, all these operations will be happening in parallel. So basically this matrix multiplication operation or the multiply accumulate operation, that is very, very important as far as our neural net implementations are concerned. So that is what is again making our Memristors very popular. So if you look at, okay, so these are all quite famous neural net implementations for speech recognition, CNN implementation, NLP, things like that. So whatever is shown in red here, these are representing the matrix operations implemented or matrix operations which are required in the implementation of this new neural network. So you'll see like most of the operations, they are matrix operation. So if we can optimize this matrix operation or matrix multiplication, basically somehow, the overall performance of the net will improve. So that is where people are becoming more and more interested in Memristor. So what happens in Memristor is, as I said before, it can memorize its resistance value. Okay? How we give a particular resistance value? We give a particular resistance value by some means of programming. You can think like that. Okay? We are applying a certain voltage across the Memristor, and how much resistance it will have depends upon how much voltage you are applying and for how long you are applying the voltage. That is what is basically deciding the memristor value. So here what we are doing, we know we have some weights values here which should be multiplied. And I will design something called a memristor crossbar array. So it is nothing but a crossbar switch, you can see. And wherever I have a wire crossing another wire, I have a memristor here. This is again 3D. Okay? These wires are actually not touching. They are stacked one above another. Yeah, in the first figure you can see. So basically these two wires are connected through the memristor. So after neural net training, whatever weight values I require, I'll be programming these memristors, or I'll be setting the resistance values of these memristors proportional to those weight values by programming them. Then this V1, V2 up to Vn, that is basically representing the X values here, which are basically going into the neural network. I'll be applying the same values here. So now what happens? This crossbar array, this is actually directly implementing the dot product operation. So this voltage here, that will get multiplied by the conductance value here. So basically the current coming out of this memristor will be proportional to the product of this voltage and the conductance of the memristor. Now, if I sum up here, this final current here, that is actually proportional to the dot product between these inputs and these memristor values. So input voltages, they are basically representing the input to the neutral network, whatever feature I want to give to the network. And the memristors, they are representing the weight values. So in one shot, I can do the entire metrical operation. And this will, the throughput of this memristor implementation, it is much, much higher compared to our traditional memory-based implementation of the same neural network. So that is what is making memristors very popular. But now, okay, and this is kind of in-memory computing. Here also you can see the matrix operation that is not happening in your CPU. That matrix operation is actually happening in a memory, which is built using memristor. Here you can think like each memristor here that is storing the weight value. Now the interesting thing is these values can be any value. So this is more like an analog device, you can see. So it can store any resistance value between a minimum value, which we call like an R off value, and a maximum value, which we call like an R on value. So it can store any value between this, each memristor here. So it's acting more like an analog device, not like our traditional ones and zeros. They are not storing ones and zeros here. They are storing some value, some analog value, which is corresponding to the weight. Now the question here is, okay, if they are that good, why we are not seeing implementation using memristor? You will hear or you will see tons of papers which are discussing implementation of AI using memristor or basically using in-memory computing. But practical implementations, they are yet to be seen. So HP Labs, they have recently claimed that they have developed the first memristor chip array, but commercially not yet produced, okay? Because a lot of challenges are there in this implementation. One major challenge is because this is acting more like an analog device, integrating hundreds and thousands of memristor inside a single chip is very difficult. Okay? So most of the work in the domain, this has been done only through SPI simulation. Practically implementing it is very, very difficult because of the analog nature of this. And we say like process variation, because you model a memristor, and when you give it to a foundry to manufacture it, even if slight variation in the manufacturing process will totally change the behavior of the device. The VA characteristic will be totally changed. And when you try to integrate hundreds and thousands of such memristors into a single chip, the effect is quite high. That's one reason we are not practically seeing it. But recent years, yeah, there are chips with maybe 10 memristor, 20 memristors coming, but not more than maybe a few hundred. We haven't seen them yet, but hopefully will come. Another challenge is, yeah, integrating this kind of analog memory with a digital infrastructure. Okay, if you want to put this thing to a traditional computer, it is quite difficult because here also maybe the weight values I am representing using these memristor values, but the inputs here, they should be also represented using some voltages. Now, if I integrate it with a traditional system, the input values will be binary in nature. So what I will have to do, I will have to use a digital to analog converter to get the corresponding voltage values here before I integrate it with the memristor-based memory. So that's also a challenging thing. Maybe that also brings extra cost also. And this is optimized for specific applications. So the crossbar array that I have shown here, this is specialized for matrix multiplication. Now, if you want to do some other operation, okay, in AI, this makes sense. For neural net, matrix multiplication is very important. But if I do some other operation, maybe let's say FFT implementation, There, I'm not much interested in matrix multiplication, but maybe I am more interested in some kind of different kind of convolution operation. In that case, I will have to change the whole architecture of the chip. So it's not like our traditional memory, which can be used for storing any kind of data. Here also data can be stored, but if you really want to implement the processing, the architecture of the memory itself has to be changed. So that's again quite challenging. So that's one reason why we are not seeing much of Memristor-based implementation. Not only if you discuss other kind of modern memories, you will be seeing the similar kind of challenges also. In RAMs, PCMs also, similar kind of challenges are there. They might have certain advantages, but drawbacks are also there. So not in immediate future, but at some point they will become very practical. But what I am trying to explore is what can be done in our immediate future. Okay, so for that, I'm again going back to our FPGA-based accelerator. So I discuss in-memory computing till this point to show two things. One is why in-memory computing is interesting. They have significance actually. And what are the new memory technologies which are proposed for implementing them. But what are the drawbacks of them? Because of that, we cannot currently practically do them. Maybe research perspective, they are much more interesting. So now I am trying to explore what can be immediately done. And for that, again, I am proposing to use FPGAs. So FPGAs, they may be used like some kind of pseudo memory. It can store data, of course, and it can process data also. So memory can be implemented in FPGA. Processing can be also implemented in FPGA. So I'm trying to use this FPGA like kind of pseudo memory, and using that pseudo memory, I'm trying to implement in memory computation. So before going that, I don't know whether it was covered when you discussed FPGA accelerator. We can have two kind of accelerator. Not only using FPGA, any kind of accelerator. Broadly, we can classify them into two. Okay, one is called this tightly coupled accelerator or TCA model. Other one is loosely coupled one. So in a tightly coupled accelerator, what happens? Like in the figure, you can see the accelerator is sitting within the CPU chip itself. So sometimes what we do is we make the accelerator part of the pipeline itself, the processor pipeline itself, and there will be special instructions which will activate or deactivate the accelerator load. Okay. So this is very tightly coupled because it is on the chip itself. So if you look at like our Apple Bionic chip, you know there is a neural net inside the processor, A10 processor. Right? So that's the example for tightly coupled accelerator. Accelerator is within the chip itself, and in many cases, it is part of the processor pipeline itself. Now, traditionally, this is not how our FPGA accelerators work, because we cannot couple an FPGA like this with a CPU. Okay. But there are newer chips, maybe you have seen this. A piece of chips where you have FPGA and processor coming together within a single package. I'm not talking about that. There also the fabric is not part of the pipeline. The fabric, FPGA fabric is sitting separate, processor is sitting separate, and it is not part of the pipeline. So we won't count it as tightly coupled. So where we usually use FPGAs is in this architecture, the loosely coupled architecture. So where we will have our CPU sitting and all the associated circuits of the CPU, and we have the accelerator sitting on some kind of bus. So in the modern systems, our FPGA accelerator that will be sitting on the PCI Express bus, PCIe, which is one of the fastest buses currently available. So the new accelerators, they will be using like Gen 4 PCI Express, which can give like maybe 10 gigabits per second throughput per lane. Like that, there will be like 16 wires and all. So this is where current FPGA accelerators are used. And their drawback, I already mentioned to you before. I have to do data movement between the main memory and the FPGA. So I transfer data from my main memory to my FPGA using some DMA controller, and FPGA will process it, and it will send it back to the main memory using the same DMA controller. So FPGAs are doing it quite fast, but because of this data movement, there could be more time. Total throughput may be reduced. So what can we do about that? Okay. Yeah, so again, this is an example for FPGA-based accelerator. So I'm working on this platform now, so that's why I have put it here. This is called the Xilinx Alveo FPGA accelerator card. So here you can see, like, this is the PCI Express Edge connector, and we'll be putting it on the motherboard, directly the accelerator. And we will have our neural net inside the FPGA here. FPGA is there under this. It's like a heatsink kind of thing. And we will process it there. Now, if you look inside the FPGA fabric, we can find like there are many things inside an FPGA. So mostly there are three things. One is called this CLB. Another one is called this DSP. Another one is called this PRAM. Again, maybe in the courses you have seen it. So CLB, called as the configurable logic block, they are used for implementing our logics, right? Your AND gate, OR gate, whatever digital circuit you want to implement, they can be implemented using CLB. Now DSP, this is digital signal processing or processor. These are again small things inside FPGA which are specialized in signal processing, usually multiplication. These are like small units which are used for multiplication and accumulation also, MAC operation. So these two things we already have. In addition to that, there are a lot of small memory, again, volatile memory, but SRAM based one, quite fast one, which we call as BRAM, block RAM. So if you look at the size of this typical memory inside the Xilinx FPGA, there will be like 18 kilobits, these are bits, okay, or 36 kilobit, each block here. But there will be hundreds of them, which will give you, okay, some amount of memory, but not in gigabytes. No? It will be a few megabytes of memory. That's also available in FPGA. Now here, what can I do? So if I want to implement neural net, I can quite efficiently implement them using this DSP as well as this CLBs. Okay, so all the multiplication operation, everything I can efficiently implement using this DSP. If I want to implement the activation function or the control circuit, I can implement using this CLB. Now, another advantage is the weight values which are required by my neural net. They can be stored in these block RAMs, these internal memories. Okay. Now, by combining them, I can make very powerful neurons. And how many neurons I can implement? This I told before. That depends upon how big your FPGA chip is. So of course, you cannot implement millions of them. Maybe you can implement hundreds of them, neurons. So that will give me quite good performance. That implementation like that. But again, drawback is newer algorithms, they do not work with hundreds of neurons. They require several thousands or even millions of neurons. So how can I do it? So I cannot just go and keep on increasing the size of the FPGA due to the same reasons we discussed before. I will have to leave with the same FPGA chip, but somehow I need to increase the capacity of the chip. Okay, so that is where we have this concept of so-called partial reconfiguration. And this is where I mostly work on. So partial reconfiguration, this is a very interesting technology. So again, if you have used FPGAs, you know what you do. If you want to implement something on FPGA, you will write the Verilog VHDL code, whatever, you generate the bit stream, you program the chip, and you use it, right? So that's the traditional flow. Now, in case of partial reconfiguration, what happens is you will not be reprogramming the entire FPGA. Instead of that, you will be programming only the part of the chip. Okay, so here you can see I have a FPGA fabric, entire chip logic is here. If I want to change some part of this fabric, what I can do is I don't have to reprogram the entire FPGA. I can reprogram only one portion of the FPGA. And when I am programming that part of the FPGA, the remaining part of the chip will be still operational. That's the main advantage. Okay. So here I am showing some example. So what is shown here is basically time multiplexing of FPGA. So I have one portion of this FPGA, and I am implementing different circuits on the same part at different time instances. Okay, so here also I am doing the same thing. So how can I exploit for this neural net implementation? So neural net, yeah, figure I have shown you before. So how can I do it? Or what can I do with this to increase this capacity? So this is the technique we will be using. So instead of implementing this whole neural net in one shot on the FPGA, at one time, maybe we will keep only one layer on the chip. Okay, so we will inject the data. We will have all these neurons in the first layer in the FPGA. He will process it. He will give the output. But this part is not there inside the chip as of now. So what should I do? The result from this layer, I should somehow store it somewhere. For storing that, I have block RAMs inside the FPGA. So I will be storing these intermediate results in the block RAM itself. After that, what I will do, I will reprogram the part of the FPGA which is hosting this circuit with this logic. Then from this internal memory, I'll be feeding the intermediate output here. He'll be giving me the result. I'll be again storing them in this intermediate results in the block RAM, and I'll be programming with the next layer. So using this technique, I'm not bounded by the logic capacity of the chip. I can implement huge. I have no limit at all, actually. Practically, there are other factors. Otherwise, I can implement any neural net with any number of neurons. And what is the price you are paying? You are paying a price here because the time required for changing the circuit, or basically reprogramming a portion of the FPGA, that will consume some time. Okay. So again, that will be in the order of microseconds, actually, the time required for changing that circuit. Okay. So the impact is not that huge, provided that is done properly. Again, I will give the link to the videos where you can see like how it can be done using some custom circuit. It can be done quite fast. So if I follow that, I can get much better performance. Now, the other issue that I discussed before, basically moving data between the computer and the accelerator card. That can be also solved using this partial reconfiguration technique. So how I am going to do it? So what I will do is, as I mentioned before, I'll be storing these weights inside these block RAMs. Okay, and for a trained neural network, the weights are not going to change. Once they are set, they remain as such. So what I will do is, I'll be generating so-called the partial bit stream. So the bit stream which I use for programming a part of the FPGA, that is what we call as this partial bit stream. So I will pre-generate this partial bit stream which already contains those weight values. Once I do like that, the advantage is my FPGA accelerator card this has non-volatile memory also. In addition to FPGA, it has its volatile memory. In addition to that, it has non-volatile memory also. So all these partial bit stream which has those weight values, I'll be storing in this non-volatile memory. And when the system starts, I'll be taking these weight values from this non-volatile memory directly to FPGA, which is quite fast compared to transferring it from the main memory of the computer to the FPGA card through PCI Express. So that will also help me to speed up my processing. Okay, I think I'm crossing the time. Okay. So basically, what I propose is to use FPGAs as devices for pseudo in-memory computation. Okay, so it has memory, it can do computation, but it is not really the kind of in-memory computation that is being proposed using Memristor or RRs, things like that. But this guy, he can emulate similar behavior, and this can be incorporated in our existing infrastructure, and we can achieve better performance. Okay, so the examples of this, how this can be done, again, I have this YouTube channel, so I have already put this pre-recorded videos. So I will encourage you to go and have a look and try them out. For doing them, you don't require Alveo, but of course, same thing can be done using Alveo also. For doing them, maybe any FPGA code will do if you actually want to do it on hardware. Of course, you can simulate, but if you want to do it on hardware, any Silence FPGA is sufficient. Okay, so I will stop here, and if there is any question, I can take. Thank you. Okay. Yes. Okay, so if there is nothing, I will stop here.
Thank you, Vipin.
Thank you.
No questions from anybody so far?
I thought like there was too less content, but it seems like I kept on going. But yeah, so maybe if you try it, actual one, that maybe you have doubt, then you can definitely contact me.
So maybe if you can share your slides, then maybe
Slides.
we will take a look at it and come back to you if there are any questions. Okay.
Sure.
All right. So if there aren't any questions, then thank you and look forward